Welcome back to the next video, everybody. Today we're going to be looking at passage to the limit. So this is more or less a direct sequel to the previous video. So definitely please watch that first. The setup is this. So A will be a coefficient lambda algebra, which is P torsion free. We'll let rho from GKS to GLN of A just be some continuous representation whose residual representation is absolutely irreducible. So we have universal deformation rings and things like that. We'll let rho n from GKS to GLN of A mod P to the NA be the reduction of rho mod P to the N. We'll denote by A sub n the algebra A mod P to the N. We'll assume we have a global Galois deformation problem D, as in the previous video, where each rho n here is of type D. As a remark, there is an analogous treatment of what we're about to do in the case that we have a global Galois deformation problem with fixed determinant, obtained by replacing end v's that we see from here on out with end v circles throughout, so trace zero endomorphisms. So I won't write that up explicitly, but just keep it in mind. Okay, so remember, A maps from Kähler differentials to AN are isomorphic to H1 of GKS and AN VN. So this is kind of a big thing that we had a couple of videos ago. If we move down to the subgroup H1 sub D corresponding to the deformation problem, that's isomorphic to A maps from omega of R sub D over lambda to AN. Okay, so basically moving to the cohomology subgroup we care about, H1 sub D, is the same thing as moving to A maps on the sheaf of Kähler differentials over the associated universal deformation ring to the type D problem we're working with. Okay, so we have this. So this works for each n. So then you might ask, can we move to some kind of limit here? Like, yeah, we can set up the A sub n's as a direct system of A modules. Okay, and then we can likewise set up the n sub A sub n's of the V sub n's to form a direct system of GKS modules. Okay, and so if you do that, you end up getting that the limit of the A sub n's is nothing but A tensor product over ZP of QP mod ZP, and the limit over n of n sub A sub n of V sub n is nothing but n sub A of V tensor product over ZP QP mod ZP. So proposition 27, there is a commutative diagram for each n given by the following. So we have A maps from omega R over lambda tensor A to AN. We already know that's isomorphic to H1, GKS, n sub A sub n of V sub n. We can also take this isomorphism and we can replace n by n plus 1, which gives me this row here in the square. But then remember, we have these directed system maps. And so you can ask, does this square commute? And the answer is, of course, yes, it does. So the proof of this is in CSS page 297. It's kind of just like, well, you can just do a brute force, but then there's also some tricks you can use to make it faster if you don't want to do a brute force. Okay, how about the limit of this right-hand system here of cohomology groups? Well, cohomology commutes with direct limits, right? So we have necessarily that H1 GKS and AV tensor product over ZP of QP mod ZP must be the direct limit of the right-hand vertical direct system. Okay, just by how this is set up. And so then it's like, well, what happens if you move to the H1 sub D in the direct limit? Well, what you do is you just denote by H1D GKS and AV tensor product over CP QP mod ZP inside the full H1. You just denote by this, use this kind of standard notation to denote the direct limit of the subsystems of the H1 sub Ds of GKS and sub A sub n of V sub n's that live inside the full H1 of GKS and sub A sub n of V sub n. Okay, so this is just really kind of notation. All right, what happens when you set lambda equal to A now? So we'll return to the situation of proposition 26 from the previous video. Now let's let rho from GKS to GLN of A be a lifting of rho bar, an absolutely irreducible residual representation. We'll assume rho is type D, where D is some global Galois deformation problem. What does proposition 26 say? It says we have isomorphisms homo over lambda, omega R sub D over lambda, tensor product R sub D with lambda to lambda mod J, with H1 sub D of GKS and sub lambda of V tensor product lambda over J. What's J here? It's any ideal in lambda. Okay. And if you like, I mean, to see this explicitly, just set A equal lambda mod J in the proposition and you'll see what I'm talking about. Okay. So we have this kind of ideal theoretic interpretation of this subcohomology group. And so let's tie this all together. The map R sub D to lambda of the tensor product classifying the deformation row of rho bar to lambda is surjective because it's a homomorphism of lambda algebras. We'll let I be its kernel. So then we have this canonical splitting as R sub D modules. We know R sub D is lambda direct sum I. And there is a natural isomorphism of lambda modules I mod I squared with omega R sub d over lambda tensor product over R sub d with lambda. So we talked about this a while ago when we talked about Kähler differentials. Proposition 26 then can be paraphrased as follows. There's an isomorphism of lambda modules between this h1 sub d of gks and sub lambda of v tensor product lambda mod j that we care about from the whole direct system setup with just lambda maps from I mod I squared to lambda mod j. Okay, so there's kind of an ideal theoretic interpretation of this cohomology group attached to the deformation problem. And it's kind of a simple one, actually. It's also sort of what you expect in some sense. And this works for any ideal j and lambda. Okay, you can also sort of just paraphrase some of the material from this video as just saying that like lambda maps from I mod I squared to omega tensor product over zp of qp mod zp. This is just isomorphic to h1 sub d of gks and lambda of v tensor product over zp qp mod zp. Okay, so basically things pass through the limit functorially in a nice way, in the way that you think they should. And then even like when you move to cohomology subgroups associated to deformation problems, you still get a nice, like very algebraic, like ideal theoretic interpretation of things that kind of agrees with things we know from previous videos. Okay, so we'll finish up this chapter, I believe, next video by collecting some local deformation conditions and kind of applying the material of chapter 8 to that situation, to those various situations. So I'll see you then. Thanks for watching.